Welcome to our international and local guests to day 3 of the HPC Roadshow. Remember that you can still submit questions to our experts using the Q&A tool, and we'll answer as many possible questions after each presentation. Now it's my pleasure to introduce Matthew Foley, Director EMEA Field Applications Engineering at AMD, who will be sharing with us why AMD is EPYC. Matthew, over to you.
Thank you, Chris. So greetings everyone. My name is Matt Foley and I manage the Field Application Engineering staff for AMD in Europe. And as mentioned, the purpose of today's presentation is to introduce the EPYC 7002 series processors. The code name for that product is Rome. And really why HPC is EPYC, if you'll pardon the pun, and what's going on at AMD and how you can take advantage of the resurgence of AMD as well as the better economics that we're bringing to the high performance computing sector. So just a real short thing about in terms of how HPC is powering some essential business. What we're finding and what we're seeing in the market is that the HPC market is a bit different than it used to be. It used to be mostly universities or government labs, research institutions. But what we're finding is that more and more commercial entities need to do modeling, they need to do product development. And so more of the on-premises market for computing is becoming high-performance computing. More of these are high-performance clusters to solve scientific problems that are needed for product development. And as we've entered this market and as we've moved forward in it, what we're finding is a tremendous acceptance of the products and a tremendous acceptance of AMD as a leading vendor in this space. And so it's just an exciting time to be in high performance computing. It's an exciting time to be at AMD in general. Now, what the processor is and what we're delivering here is really leadership across the board. And by that, we mean performance, TCO, security, architecture. And how we really think about this, I want you to first look at the slide and just look at the fact that this isn't a single die solution, right? This is a multi-chip module. That's one of the innovations which has allowed AMD to come back and move forward and move to the front of the pack in terms of processor performance and processor economics. So from a performance perspective, when we announced the product a year ago, it was twice the performance at half the cost, right, of the competitors. And the ratios really haven't changed all that much. And so from a TCO perspective, you can imagine if you're delivering that much more performance at significantly lower costs, it makes it a fairly straightforward calculation. From an architectural perspective, we're enabling different things. Not only does the processor have a modular architecture, but because of the features that we're bringing in terms of memory and I/O along with the cores, we're able to enable some different system designs, and we're able to bring forward single socket servers, which can credibly replace the dual socket servers of today. And last but not least, of course, we have security. And so this is where not only do we take security seriously, we also introduce unique and interesting features into the market. We hold those up to the scrutiny of the industry, and then we react quickly if problems are found. And so we have leadership security and a real innovative, interesting feature here of memory encryption or full memory encryption within the system. And we're now starting to see a lot of adoption of this technology as we move forward into the market acceptance of some of the things that we've done differently. Now, when we're designing new processors, it's fair to say that you're designing for advanced workloads, and all of the workloads on this slide, as you can imagine, are important. The main server design target, though, today, right now in 2020, is the cloud. It's the cloud vendors. So the cloud vendors consume over half of the server market today. So half of the processors, half of the systems go into the 7 or 8 superscaler or hyperscale vendors that you all know, people like Amazon, Microsoft, Google. And so as a result, as a supplier to that market, we have to design our processors in terms of facing that space. And what you need to compete there, you need more cores, you need high performance cores, you also need a lot of memory support, and a lot of I/O. And so by bringing forward all of these and by leading in all of those metrics, we do have more cores, more memory, more I/O supported per socket than in the industry. What we see here is that we're good at all the other workloads too, right? So not only the high performance computing, which really started in terms of our memory performance, and now it's expanded to the rest of the fields, but also machine intelligence, big data, software-defined infrastructure. Everything in this chart really depends on either more memory or more cores or more I/O. All of this has certainly helped us define and take over some specific market segments. So we're really starting to see a tremendous uptake in the cloud. We're also seeing it in hyper-converged infrastructure. We're also seeing it in virtualization, and we've been very, very fortunate and very successful in the high-performance computing space as well. So what you can see here is a bit of a customer list in terms of some of the wins and some of the notable wins that we've had here over the last couple of years. And this just continues, right? This list is by no means exhaustive, and so we just continue to provide and challenge ourselves with. We provide ourselves with the challenge of competing for these deals. So the high performance computing segment is the most competitive part of the server market. So it is the most competitive part. It's the part where you have RFPs that are written and in diabolical ways. Sometimes you also have customers who are aggressively looking forward into the future, and it's a constant game of schedule chicken, if you will. So it's a constant game of trying to put forward a credible roadmap, trying to make sure that that roadmap is something that you can support, something that you can count on and deliver. And so these customers have taken the plunge with us. We are happy to support them, and it's been certainly a good ride in the HPC space, and long may it continue. So with regards to a couple of notable systems here that are certainly worth calling out separately, the first one is called Frontier, and this system is intended for the Oak Ridge National Labs and the Department of Energy in the United States. It will be the first exaflop system deployed in 2021. And this system is a combination not only of a combination of the CPU and the GPU portions of AMD. So it's EPYC CPUs and Radeon Instinct GPUs. They are combined into a node, which is actually cache coherent between all of the parts on it. So you have cache coherency between the CPUs and the GPUs. What this means, it means an easier programming environment. What it also means, and really the ambition of all of this, is to try and figure out a way to get heterogeneous computing accessible to a broader market. So much of the work here that's going on in Frontier, aside from the hardware work, aside from producing the best processors and the best graphics components that we can, much of the work is actually a software work. How do we enable the software ecosystem to easily adapt to the heterogeneous computing infrastructure that we're putting out here? And it's not an easy task. It's a big project. It's also supported by Oak Ridge as well. And we're moving forward in this because what we're seeing is that we're able to bend the curve in terms of HPC performance. So if you plot the graph of all of the top 500 supercomputers over time, it's a pretty straight line. What we're seeing is that we're able to bend that up. We're able to improve the rate of performance acceleration. We're able to improve the rate of performance more than what we would normally have once we can make credible use of accelerators. So this is really the key of that project. In addition, there was a second system as well that was announced, and this is for 2022. So Frontier is 2021, El Capitan is 2022. It's a different lab, same department. So the lab is actually Lawrence Livermore out in California, and this is expected to be over 2 exaflops, and it's the next generation of the CPUs and the GPUs as well for this opportunity. So same thing, but what we're really doing here and what we're trying to compete and how we're trying to set the trend and how we're trying to differentiate ourselves is really by credibly providing a heterogeneous environment with both with both high performance CPUs as well as high performing GPUs, and it's very important for us to be able to deliver. Now, with all of the performance and all of the features that I'll describe in a couple of slides, I just wanted to stop here and say there is certainly proof of all of this leadership, and we have well over 140 world records according to this slide. I know for a fact it's 170 or 180 now. When we launched, it was 80, and it's only continued to grow as our market share and as our market penetration has grown. So the benchmark world record list has grown as well. And you can see, you know, from floating point applications to general purpose applications, decision support, databases, all of these things move, or all of these records have come to us. Basically, what happens is we get new workloads and we try them out, we wind up setting records. And as our penetration in the market grows, that's another area where we are, you know, we're seeing these world records fall. So right now, AMD's market share is over 10%. So we announced last quarter that we had passed the 10% market share. Higher in cloud, lower elsewhere. And so what you can see is that what we're doing with the with this is, as we get more and more adoption, and that adoption is accelerating, by the way, as we get more and more adoption, we're able to take on more and more workloads and figure out, you know, ways to get them to take full advantage of all the features that we have inside of the products. Moving specifically to the HPC market, what you see here is, this was a slide from 2018 about the size and shape of the HPC market. And the reason this was called out, this was really done in the transition between our first generation and second generation EPYC. So the first generation EPYC is socket compatible to the second generation, which means by default we have the same amount of memory channels as we do in the second generation EPYC. At the time, and even today, that is industry leading. And so as a result, we started to win in the HPC segment. We started to win in the memory bound workloads, and made significant headway in terms of the industrial PC market. A lot of the car makers here have had success with it. We've worked with racing teams. All of those types of applications, they fit well into a memory bound area. Now, with the rest of the features on Rome, with the rest of the cores, with the rest of the I/O, now we're able to compete for the entire thing. So we have improved the floating point performance by 4x. And so now the flop sensitive workloads are in our wheelhouse as well. We have improved the frequencies as well. So we're now bringing high frequency parts to market sooner than we did in the life cycle of the first generation. So as a result, we're seeing some uptick there as well. And then the balance side is kind of a mishmash of everything, but we're doing well in those spaces too. So we started with memory, we've expanded to compete effectively for the entire pie. So what is the second generation EPYC? Again, up to 64 cores, twice the performance of competing products, and half the cost. And then we have advanced security features on top of that, which are also important in their own way. So how does this work? So we like to say that we have leadership architecture, and what does that really mean? So this multi-die architecture is really fundamental and key towards the whole thing. And the reason is that one is, from a silicon perspective, the semiconductor industry is fundamentally a real estate game. The smaller the die, the better you're going to do. And by cutting up the die into smaller chips, we're able to manufacture it more efficiently. In addition, we don't have to implement everything in the same process technology. So in our products, actually the I/O is implemented in an older process and the cores are implemented in a newer one. As we move forward with roadmaps, we don't have to change everything at once. And that's a very key thing, because it allows us to react more quickly to the market. And also it allows us to reuse that technology in different markets. So we have the same cores in our client devices. We have the same security in our client devices as well. Those kinds of things we share across the markets, and it allows AMD, which is still a fairly reasonably sized company, we're about 11 or 12,000 people, it allows us to compete effectively across a far bigger market space than we otherwise would without this approach. So from a performance perspective, the performance is excellent, and it's been validated across multiple workloads, hundreds of workloads, customers, everything. We clearly do have the lead. And then from a throughput perspective, this has been key in markets like telecom, where we have had the advantage of being the first x86 processor to support PCI Generation 4. And so we're seeing this in drives, so a lot of NVMe drives are Generation 4. We also see this in the NICs, so some new Generation 4 networked interfaces, which also allow for us to address even different industries. Then, of course, there's security. We call it Infinity Guard, which is the name that we're putting onto our security products. But what Infinity Guard really is, it talks about the security that we have in terms of a trusted boot, in addition to the security that we have with regards to memory encryption. So this is the processor at a glance, and you can see there's 9 die total. 8 of them are core dies, and there's a die in the middle which has all of the I/O in there. Because of the way that this is architected, we still show up as one NUMA domain in terms of memory memory performance. We can still cut this up into 4 NUMA domains or 2 if you want, but the difference between those from a performance perspective isn't that great, and the default is 1. And the reason why is because that's the standard in the industry. That's how the Intel products behave. And so as a result of that, if we want to play in the same software spaces, we need to behave in the same way. And so that's why this is that's why we have this here. It's also just less complicated for software to deal with. Now, there's 64 cores, up to 8 cores per chiplet, and then the cache is distributed around the parts. So that's one major difference, and probably the major persistent difference that you're going to find as the industry moves forward. We're moving from monolithic caches to a distributed cache. So we have significantly more cache than our competitor, 256 meg of L3 cache, but it's distributed. And that's both good and bad. So the reason why that is bad is because software could be written such that they assume that all cores are equidistant from all cache. In practice, though, we don't really pay a penalty because we have so much more cache that it makes up the difference. And in addition, the cache that we have, not only do we have so much more of it, but there's less contention for it because it's shared with fewer resources. So as a result of that, what we're finding here is that we have excellent performance with regards to these codes, and even the opportunity to tune more carefully. So if you take processes and you pin them to the right cores and you're around the right caches, then you can even achieve significantly better performance as well. So it's the way that the industry is going in the future. We're pioneering this way, and we've done all the work to make the software work with it. From a memory perspective, 8 channels of DDR4 at 3200 megahertz, 4 terabytes a socket if you can afford 256 meg DIMMs. But we have significant amounts of memory. You can get up to 8 terabytes in a server. So performance we've mentioned. PCI lanes, there's 128 lanes of PCI Express coming out of the processor. In a 2-socket configuration, we take half of those lanes, 64, and we take 64 from the other processor, and we tie them together as the coherency link. And so what you can have is 128 lanes on a single socket system and 128 lanes on a dual socket system. We also do have a mechanism whereby we can take 1/4 of those lanes and also repurpose those for PCI Express. So you can get up to 160 lanes on a 2-socket system. And then from the security perspective, we have a dedicated security system. That's what the secure processor is. It's actually an ARM core on the process, on the I/O die itself. And it maintains not only the security posture from a secure boot perspective, but it also generates encryption keys, which are then used by the memory controllers to encrypt memory as it's written and decrypt memory as it's read. And then we have additional features on top of that in order to dedicate different keys per virtual machine. So just more on the chiplets and how this has evolved and how this is a hybrid and multi-die design. And you can see here in the traditional monolithic sense, you would have to guess everything right. So from a development perspective, it's harder. And the reason why is because you have to have the right number of cores, you have to have the right cores, you have to support the right memory standards, the DDR3, DDR4, DDR5, same thing for the I/O. You have to guess all of that right. And then the other thing is that from a manufacturing perspective, it's actually harder because it's a bigger die. And so it's more difficult to get a bigger die to yield. Whereas in our approach, in EPYC here, we've got a lot of small dies and we mix and match them with what we call the infinity fabric, which is a cache coherent bus that's in the part itself. And by doing that, it allows us to produce smaller dies, which gives us an advantage in terms of manufacturing as well as cost. It allows us to mix and match technologies. You can imagine if we have a core ready, like Zen 2 to Zen 3, if we have a core ready, maybe we'd want to change the cores and not change all of the I/O standards behind it, not have to redo all of that work. And so you can see where this mix and match ability allows us to be far more flexible. We can even take some of these core dies and put them in a desktop package if we want to, and we've done that as well. So this allows for significant technology reuse, and it allows us to be infinitely more flexible in terms of how we can configure this in order to better hit sweet spots in the market. We don't have to have all these chiplets in the package. We can get by with 4 or 2 or 6. We can also change the amount of cores that are active per die, and that changes the ratio of L3 cache to the cores. So it's important to know that we have this kind of flexibility, and that'll be important going forward as well. From a floating point perspective, I won't spend too much time on it. The second generation doubled the floating point width of the first, and as a result of doubling the floating point width and doubling the cores, that's why we have 4 times the floating point performance in Rome than we had in Naples. And so this has worked well. This has generated, you know, close to 4 teraflops in high performance LinPack for the top end SKU and on a dual socket configuration. So it's a tremendous, it's been a tremendous benefit for us. And this, of course, is part of the reason why Rome and why AMD has now been able to address all of the HPC market instead of just the memory bound space. Speaking of memory, so we do have different, we do have a memory difference there as opposed to our competitor as well, because we have 2 more channels. And now because we can support faster DIMMs, we can have up to 45% improvement in terms of memory bandwidth per server as opposed to our competitor. So that's the reason we support faster memory, and the 2 more memory channels does make a difference. This is the SKU stack. So you can see here we have SKUs ranging from 8 cores all the way up to 64. Everything in white is a dual socket configuration. So everything in white you can put into dual socket servers. Everything in blue is intended for single socket servers. Now they do work in dual socket motherboards, but only alone. The point of it is, though, is we were trying to emphasize and give a jump start to the single socket server market. So those parts are available at a bit of a discount. Also, the other thing to note about AMD is that we don't play games with the rest of the feature set. So every EPYC processor includes 8 channels of memory, up to 4 terabytes of capacity, all of the same PCI lanes, and the security features as well. So it's a bit easier to understand. Now, in terms of what this drives, so on a single socket server, we can actually outperform most any competitive dual socket system. And then for the dual socket servers, we actually double that performance further. So we've got this huge dynamic range that you see with regards to EPYC, and it allows us to do a very good job with a limited number of platforms. We don't have as many platforms as our competitor does in the industry, but as a result of having so much more performance, so much more of a performance range, we're able to compete in all of those segments anyway. So this is just an example of a single socket server. You can see, you know, one 64-core processor versus a couple of 20-core processors or 16-core processors, and we're able to provide, you know, more cores, more bandwidth, more performance, lower acquisition cost, less power. All of that goes with it, and it's what you would expect, right, when you're comparing a 64-core server to something less. Now, from a 2-socket server perspective, the comparison is pretty drastic. So we have 2 64-core processors, so it's 128 cores for the whole system versus 2 28-core processors, so it's 56 cores for the whole system, right? And as a result, the performance difference is pretty stark, and the pricing was stark too. When we announced it, our distributor buy price was something like $6,900, $7,000 or so, and the price for these type of processors from our competitor was closer to $13,000 or $15,000. So there were significant differences in terms of the price performance. So basically double the performance, half the price was kind of the mantra we went with for a while. So one more thing on processor SKUs, and this is really important to understand, so I hope to just spend a couple of minutes here with regards to what we've done differently. So this is the 7F SKUs. So these are the 7F, the high frequency SKUs. And this example here is the 7F52, which is a 16-core SKU. And the thing I want you to look at is the cache per core. So you'll notice that it's 16 meg of cache per core, which is huge. It's enormous compared to competitive solutions. And as a result of that increased frequency, as well as that significantly increased cache per core, you can see that we get significantly higher performance in both SpecInt base and SpecFP base. As a result of this, these are the highest single core performance scores that you can get in the industry right now. And so this for us is certainly an accomplishment. It's a wonderful solution, and it's enabled by that architecture. So this part actually has all 9 chips in it, and each one of those core die actually has actually has a couple of cores active. So each one gets a full 16 meg of cache. So we only have 2 cores per die active on it, but we still have all 8 dies, so we can still take advantage of all the cache. Now, from a performance perspective, this is the 64 core part. So we get, 72%, 100%, 79%. This is against the top end of the socketed competitive parts. And then the same slide with the F parts, with the high frequency parts, and you wind up seeing higher per core performance, 33%, 46%. Those are different numbers that we have on a per core basis, depending on how we go. So we can go both ways. It used to be with AMD that you said, well, you got a lot more cores, but you don't have the single threaded performance. That's not true anymore. So what we have is we have a lot of cores, and on some SKUs, we can also shrink that down and provide the best single threaded performance in the industry, not only for high performance computing apps, but this also really affects databases because those tend to be licensed by core, and as a result of that scheme, everyone's looking for the highest performant core that they can find. So this is just an example here from the weather, the weather SKUs as well. So we see significant performance, and if you looked at the initial customer list that I showed in the beginning, there were some weather services and weather centers on there, and this is why we won those. And the reason is because we have a faster time to model, we have really good scaling, and it's just a better deal. So with that, towards the end here, wanted to close with the security piece. So we call this AMD Security Guard, and what you can see, there's the secure root of trust technology. This is done with the secure processor. That's fairly standard now. What's different is secure memory encryption. So the secure processor provides a key which actually goes to the memory controllers, and the encryption is done on the memory controllers. In this operation, the software is completely unaware that this is happening. There's no interaction with the software on the machine at all. Secure enterprise virtualization is different. This is where a hypervisor can interact with the secure processor, generates a list of keys, and then the hypervisor assigns those keys to the various virtual machines, and then those virtual machines can each use their own key. So all the memory is still encrypted, but each virtual machine is also cryptographically isolated from each other. This technology is available today in the Google's confidential computing. So they have recently launched this and made this a priority in their activities. What this does is it fundamentally closes the last memory hole out there from a security perspective. You always had this problem of memory in use wasn't encrypted. Well, in this case, memory in use is encrypted, and not only is it useful for servers, it's incredibly useful for clients. You can imagine if your laptop has this feature, you can put it to sleep, lose it at a restaurant, and you won't have to worry about somebody being able to scrape the memory and make any sense of it. That's the other use case, and it also demonstrates how we share technology between markets. Last but not least here, we have a stronger ecosystem in EPYC than AMD did have in Opteron. So just to give some perspective, for those of you who remember AMD, we've got a significant long history. We're a 50-year-old company, and about 15 years ago, AMD was about 25% of the server market, and that was based on the strength of the Opteron products. We did not have as many systems with Opteron as we now have with EPYC. So we have a growing ecosystem, a large, diverse ecosystem, and a lot of the industry is really betting with us that competition in this space is worthwhile, and the competition in this space is going to be successful and going to be continuous and sustainable for the long term. So this is our roadmap. You can see 7001, 2, Milan, as you might imagine, would be 7003. So this is Zen 3. This will be coming out next year. And then from the GPU side, you can see we have the MI25 and the MI50. Those are in market today. And the MI Next is out later this year, early next year. So from a software support perspective in the HPC space, that's always important. We have our own compiler. We also base it on LLVM. We support GCC. We do work on the Intel compiler and the Intel libraries. There are some additional settings you would need in order to get the full advantage of what we can provide. But nonetheless, we are standard from an x86 perspective, and so you should expect the software to be standard as well. We adhere to that. We're part of that consortium, and so that are part of that ecosystem and a full participant in it and contributing instructions even. So that's what you should expect, and we do have the tools to enable you to be successful. In addition, on the AMD site, you can see some of the HPC tuning guides, as well as a lot of the references to some of the applications that are popular in this space. We maintain that library, and it's constantly growing and constantly changing. And so just in summary, what you'll find from AMD, we have the world's highest performance x86 server CPU, and certainly in the socketed space. We do have world record performance from a floating point perspective. We have significant benchmark wins in all sorts of commercial HPC applications, as well as non-commercial HPC applications. And we're powering the fastest exascale systems, of course, that have been announced. So it's an exciting time to be at AMD. It's an exciting time to be in high performance computing. And with that, I will take my leave of you. So thank you very much for your time and attention today, and I look forward to your questions.
Matthew, thank you for that. Always great to hear from AMD and from yourself. So we've brought back David Power from head of HPC to have a chat with you around the AMD, to have a chat with you around AMD. So David, I hand it over to you.
Thanks, Chris, and thanks, Matt. Excellent presentation. So I'm quite excited about these X-scale systems that AMD had announced. Have you any more details you can share about, architectural improvements and, the overall sort of balance of these systems in terms of GPU, CPU, and even the interconnection between them?
Certainly. So thank you. It's good to hear you both again. So thank you for the opportunity to be a part of this event. With regards to the exascale systems, they're a combination of our CPU and GPU technology. In practice, I talked a bit about it in the presentation about the Infinity Fabric, and that is the cache coherency fabric that we have within the part. When we extend that externally, we also call it XGMI, or the Extended Global Memory Interconnect, and it becomes the cache coherency bus between the two processors in a dual socket system. We use that same Infinity Fabric and cache coherent link to connect GPUs together. So if you're familiar with NVIDIA, with NVLink, we have a similar structure here with the Infinity Fabric to allow the GPUs to be formed into hives. And then the next step of that would be to use the same fabric to provide cache coherency between CPUs and GPUs, between different kinds of processors. And by doing so, the objective is to make the entire heterogeneous compute complex easier to program. And so in the two large exascale systems that have been announced, so Frontier as well as El Capitan, part of those wins are significant efforts in software to make these types of structures easy to program, or easier to program than they are today. And so those are the areas where we're really making the heterogeneous computer, or heterogeneous compute model very real and very accessible. So for us, that's the way forward. And the nodes in Frontier, for example, as has been shown, are a single CPU with 4 GPUs around it, all connected in a cache coherent fabric. And that's the module really, and it's just a collection of those modules makes up the machine. But the key really is this cache coherent heterogeneous compute model, which will be really one of the first implementations of that in the industry.
Excellent, excellent. And can you tell me a bit more about the software development environment for these next generation GPU products? Is there anything out there today that end users can go take on and work on, so that they have something that's transferable onto these next generation of systems when they become available?
Yes, there is, and the software development is called, or the software development environment is called ROCm, so it stands for Radeon Open Compute. This is our open source GPU initiative that we've had for a while now, and we're moving. We're in ROCm 3.x now, 3.4, 3.5. And we'll have ROCm 4 coming out at the end of this year. We typically launch those during the supercomputing conferences in November. And so what this is it's available on GitHub, and some of the interesting parts of it. One is we're upstreamed in TensorFlow and PyTorch. So from a machine learning frameworks, we have the support there available already. The other piece that gets the most attention is a translation language. It's called HIP. So it's a heterogeneous instructions for portability. And so what this is a language that's intended to really translate from CUDA to a language that the AMD GPUs can understand. And so similar to how we are in x86, and that we are a challenger and we have to fit inside the market structures that have already been defined. The same is true here in the GPU space. So NVIDIA has made significant investments there, and we are in the process of providing competition in that space. So what we have with HIP is you can take CUDA code, you can translate it into HIP, and it's a fairly straightforward process. And from there, you can maintain a code base that you can then compile onto either type of GPU. So we're hoping to pick up the applications that way. We're also providing major efforts to port specific HPC codes like GROMACS and others to our GPUs as well, so that we can provide tested and validated example codes for running those applications on our GPUs as well. But in order to get started with it, in order to see it, ROCm is available, and it's there on GitHub today for download.
Brilliant. So that's excellent progress. And especially since there's an active initiative from AMD to actually work with the end user codes and assist with porting those over. I don't want to suggest that end users are lazy, but it's often a path of less friction if there is already a pre-accelerated, be it a function call or library that can plug into those applications. Will AMD be sort of maintaining a public list of applications that are accelerated that users can check in on from time to time as this list grows over time?
Yes, we will have. We will. It's similar to how we're now public with our TensorFlow and PyTorch activities. As we get more into these codes, we'll be able to share the versions that have been successfully ported over to the AMD architectures.
Brilliant. I look forward to seeing that. Okay, excellent. I know, Maz, maybe you've one or two final queries to wrap up the session with.
Thanks very much, Dave. Yes. How does the performance compare to similarly priced Intel processors?
So from an EPYC perspective, when we launched at the top end of the stack, we were literally 4 to 1. So we were twice the performance at half the cost. So the price performance ratio was four times better. Across the balance of the stack, we average anywhere between twice the price performance. So you either get the same performance at half the price, or twice the performance at the same price. We tend to go either from 2 to 4, depending on the list prices and how they evolve over time. But that's typically what it's been and what we've seen in the price bands. Of course, pricing is always a topic, and it can be an individual topic as well. But that's what we've seen in the list price area.
Another question here. Do AMD EPYC CPUs run hotter or use more power compared to Intel?
We don't really, I would say no, in that we all have defined thermal design envelopes, and so we fit within those. So in the AMD case, the TDPs are actually a hard limit. And they're also configurable, so you can configure those as well. But in terms of, in terms of like performance per watt, we're ahead of our competitor. And the reason for that is just because of the advanced process technology that we're able to use. So AMD EPYC and the compute dies in the EPYC processor are built on the 7nm process. And from a semiconductor perspective, it's always smaller, faster, cheaper, lower power. And that's the case here. So as we've taken the process lead, the power efficiency has improved, and as a result, we're actually more efficient on a performance per watt basis as well.
And then final question, I think someone just can't understand how you can get so many more cores in a smaller die.
That's kind of the magic of the semiconductor industry, right? As you move towards more advanced process nodes, the numbering means, the 7nm is an attempted description of the line width of the feature inside of the part. as manufacturing has become more and more complicated, it's maybe less and less true that that's what it is, but it's still a guideline. And so the smaller the feature set means that you can actually fit more cores into the same space. And every die shrink used to be about a 50% improvement or a 100% improvement. You could get twice as many dies on the same wafer. And so as a result of that effect, the reason we can cram more dies or more CPUs into those packages is because the feature widths of our semiconductors are smaller than our competitors because we're using a more advanced process.